Good day, ladies and gentlemen. Who is ready for some high-powered calculus? I know I am. Let's get into this. Today we're looking at finding the derivatives of exponential functions as well as logarithmic functions. They're very much related to each other as they're inverses of each other. In one of my previous videos, I talked about the number e and where that comes from. What we're going to start out by doing is deriving the derivative of e to the x. And e to the x is just a special case of any exponential function, a to the x, where a is some real number. Let's find the derivative using first principles. So dy dx equals limit h goes to 0. This is where all derivatives really start. A to the x plus h minus a to the x, that's f of x plus h minus f of x, all over h. What happens as h goes to 0? We can't substitute it right now, so we try to simplify things. And this first term can be written as a to the x times a to the h. So now both terms in the top have an a to the x, and we can factor that out. Limit h goes to 0, a to the x times a to the h minus 1 over h. Okay, well, the a to the x isn't dependent on h at all. That's effectively, it remains constant. It remains a to the x. We can factor that out times the limit as h goes to 0, a to the h minus 1 over h. And you might be saying, how do we deal with the numerator now so that the h in the denominator can divide out and we can do a direct substitution? Well, we can't right now. We don't have the skills to deal with this limit, but I ask that you trust me that this limit right here does exist. It is equal to a number. So this derivative is equal to k, the limit of that, times a to the x. Okay, so great. This is awesome. What good does it do us? Well, what if I wanted to know what's the derivative with respect to x of a to the x evaluated at x equals 0? Well, here's our derivative. What happens if we evaluate this derivative at x equals 0? It's just equal to that k. Cool, stay with me here. So what if k equals 1? So I want to know where is the derivative when evaluated at 0 equal to 1. So sort of what I'm thinking here is, what kind of value for a is dy dx of a to the x equal to 1 times a to the x? Because when we're evaluating at 0, the a to the x now becomes irrelevant. So what kind of a value is going to give us this? So what we're looking for, what we care about here is this limit as h goes to 0 from up above. The limit of a to the h minus 1 over h, we want that to equal 1. And for some very small h, a to the h minus 1 over h is approximately equal to 1. And the smaller the h, the closer we get to 1. Isn't that what limit means after all? So, for all intents and purposes, a to the h minus 1 equals h, and a is equal to 1 plus h to the 1 over h. And if you've paid attention to where e comes from, this might look a little bit familiar. Let's let h equal 1 over m. So in other words, small h means large m. So the smaller h gets, the larger m gets. And so what we have is a the base of that exponent, is equal to the limit as m goes to infinity, because as h was going to 0, m is going to be getting larger. 1 plus 1 over m to the m, well, that's the definition of e. So, big time here, if y equals e to the x, dy dx equals e to the x. The function e to the x, the exponential function, is what we call an invariant function. Under differentiation. So from this point forward, there should never be any question about what the derivative of e to the x is. It's itself. But if you should need it, make sure you're checking your formula book because it is there. Moving on to natural log. Let's find the derivative of this. To do this, let's rearrange this function. Let's solve for x. So x is equal to e to the y. We just talked about how to find the derivative of e to some power. So let's take the derivative with respect to x now. So 1 equals, now derivative of e to the y is going to be e to the y, but times dy dx, implicit differentiation. And then dy dx is equal to 1 over e to the y. Well, what did we call e to the y? E to the y was just x. So the derivative of natural log is 1 over x. Cool, nifty. Here we go on to our next function. We're going to go back to the generic a to the x. We established earlier that this is equal to k times a to the x. Let's figure out what k is. So we start with y equals a to the x, and again, we're going to use some of the stuff that we previously just figured out. I'm going to take the natural log of both sides. So now we have natural log y equals x natural log of a. And natural log of a is just a constant, remember. A is a number. So the left side derivative is 1 over y dy dx, derivative of natural log times the differential of y with respect to x equals 1 natural log a. If it was derivative of 3x, the derivative would just be 3. So dy dx is equal to y natural log a, but y was just a to the x. So that constant, that k value, is the natural log of the base. And again, this derivative rule is provided for you in your formula book. Next derivative is the log any base of x. We found the log base e, we took the derivative of that. Let's take the derivative of any base. So similarly to the natural log, we're going to rewrite this in exponential form. X equals a to the y. Take the derivative with respect to x. So we have 1 equals a to the y. Natural log a, that's the derivative of the power a to the y, but times dy dx. Because implicit differentiation, the variable in the exponent wasn't x, it's y, so implicit differentiation. And now we solve for dy dx. 1 over a to the y, natural log a, equals dy dx. So dy dx is equal to 1 over x times natural log of a. And again, guess where you can find this? In your IB formula book. It's provided for you. It's a wonderful thing. So let's try one on your own. Let's see how well you can put these rules together. Let's say y equals x to the x. I want you to find the derivative dy dx. So pause the video right now and give this a try. Okay, well, to do this, let's forget about just getting dy dx by itself right away. We're going to do, similarly to one of the previous derivations, we're going to take the natural log of both sides. So now we have natural log y equals x natural log x. And this is what we'll take the derivative with respect to x of. So derivative of natural log y with respect to x is 1 over y dy dx equals right-hand side product rule, x times 1 over x, first times derivative of second, plus second times derivative of the first, which is just 1. Okay, so dy dx is equal to multiplied by y on both sides. Well, y was x to the x, times that becomes 1 plus natural log x. There's our fun derivative of x to the x. All right, another example. We have the function y equals e to the x. I want to describe that, and I also want to find the equations of the tangent and normal lines at x equals 0. So in other words, describe it. Tell me, is it increasing, decreasing, concave up, concave down, that sort of thing. So I want you to pause the video and see if you can come up with a description for this. Then restart it and see if your description agrees with mine. All right, first piece of the description. Take the derivative. The derivative is e to the x times e to the x. We're using the chain rule. That function for all x's will always be greater than 0 for all x's in the reals. So that means since it can't equal 0, there can't be any maximums or minimums. And because it's always positive, the derivative always positive, that means the function is always increasing. So we know that y is a strictly increasing function. If you haven't gotten the description about the concavity of this graph, why don't you pause the video and give it another try? Otherwise, just keep on watching. So here is our second derivative. We had to use the chain rule and the product rule, taking the second derivative. And this second derivative, it's also always 0 for all x in the real numbers. So what does that mean? It means, so no points of inflection and always concave up. Nifty, cool, excellent. Well, let's find these tangent lines, this tangent line and this normal line. Tangent at x equals 0. Well, y evaluated at 0 is e to the 0, which would be e. dy dx is equal to e when x equals 0. So our point, our equation, going through the point 0, comma e, or just y equals e times x plus e. Normal at x equals 0. Well, we're still dealing with the point 0, comma e, but now our gradient is negative 1 over e. And our normal line takes the equation y equals negative 1 over e times x plus e. Fun little equations from a funky looking equation, e to the x. So here we have it. We have the derivatives now of any exponential and logarithmic function, specifically e to the x and natural log x, but we've extended those ideas to any base that we want within the real numbers. And this is where I shall leave you. I hope you truly enjoy this.